Green's theorem is a beautiful two-dimensional theorem that is often presented before people talk about Stokes theorem and the divergence theorem. However, it turns out that it can also be presented as a quick consequence of Stokes theorem, and even though it is not terribly conventional in calculus courses to do that, there are good reasons for delaying Green's theorem, and so before we actually talk about Green's theorem, I'd like to explain a few of these reasons. So there are certain reasons to de-emphasize Green's theorem, and this is a term that used to be quite loaded in the educational community. When I say de-emphasize, I don't mean we're not going to talk about it. I'm just saying there is a theorem that is more powerful and more important, and that is Stokes theorem. So Green's theorem is a theorem that talks about two-dimensional vector fields and curves in two-dimensional space, which means for real applications, nobody can argue with that, whether we like it or not, it has one dimension too few. Classical mechanics, classical electrodynamics, any kind of classical description of physical reality sits in three-dimensional space. And so that means Green's theorem could only be applied if we have some kind of great symmetry, and by now science has advanced to the point where really three-dimensional modeling is what people need to do. Most practitioners outside of mathematics actually think of Green's identities, not Green's theorem, when they hear Green's whatever. And that actually I have asked several people about that, and they all immediately cued on Green's identities, which are very, very important. But Green's theorem, when I once described Green's theorem to a colleague in engineering, he just said, "Oh, you mean two-dimensional Stokes?" And yeah, and I think he may have said it as a question, but it could also be a statement, actually. And finally, Green's theorem actually can easily be recovered from Stokes' theorem by attaching an artificial constant z coordinate to everything, and that's in fact what we're going to do when we prove Green's theorem. So these are reasons where I'm saying, well, look, I mean, yes, it is beautiful, and Green was a great mathematician, but there are other things that we could probably spend our time with that may be worth more of our time. On the other hand, I'm not saying let's toss it out. There are reasons to retain Green's theorem. One of them is that Green's theorem is a good intermediate stage when we prove Stokes' theorem, and of course we've seen that the proof that we had for Stokes' theorem was not for the faint of heart, let's just say it that way. Of course, there is a counterpoint that I can make that can potentially brand me as a heretic, at least to certain mathematicians, which is that although we should respect proofs and work on understanding them, calculus simply is not a proof class. And then, of course, besides, we did prove Stokes' theorem directly. It was blood, sweat, and tears, but we got it done. History is another reason, and that is that even though I'm not a historian, supposedly what we call Stokes' theorem was communicated to Stokes by Lord Kelvin, actually. Stokes popularized the result, and by one account that I read, it is actually Green who wrote down the first correct proof of the result. So in some ways, Stokes was only quote unquote a broker. He was certainly brilliant in its own right, but in this particular setting, he was in some ways a broker between Lord Kelvin's intuition and apparently then the rock-solid mathematical proof that presumably came from Green, but that means of the three gentlemen, Stokes had the least claim to the theorem, I think, and his name was attached to it because people learned of the theorem through Stokes. That is how history sometimes works. Green's theorem also leads to a way to measure area by integrating along the perimeter. And that's actually pretty cool, and that's something that we're going to look at in detail, because that is something where we potentially would even have an actual application. If you have a strangely shaped area and you want to find out how much the area is, you can just run something along the perimeter and with a line integral figure out what the area is, which sounds downright strange, but we will see in the derivation that it does work. And finally, then the proof that we present here actually is also good practice for Stokes' theorem for this going from 3 dimensions to 2 dimensions. That's a philosophical thing that I have. I like to go from the more general, more powerful results to the simpler results. That is a whole lot easier than building things up from the simpler stuff to the more complicated stuff, because jumping from 2 dimensions to 3 dimensions, that is something where quite a few people will certainly tell you that is fraught with peril. Things get more complicated, and 3-dimensional space in some ways just also behaves differently. For example, the notion of simple connectivity in 3-dimensional space that we talked about in the previous presentation is more complicated in 3-dimensional space than in 2-dimensional space. Okay, in terms of Green's theorem, what does it say? It says that if you have a curve in the plane that is positively oriented, piecewise smooth, simple, and closed. So we know, again, technical hypotheses, okay, it shouldn't self-intersect, it ought to be closed. Piecewise smooth is the really technical part, and then positively oriented, just we're going around it counterclockwise to have the right orientation. And if D is a region in the plane that is bounded by that curve, and P and Q have continuous partial derivatives on an open region that contains D, then the line integral of the vector field PQ along the closed curve C is equal to the integral over the region D of dq dx minus dp dy as an area integral. And you may say, well, that looks like Stokes. Yeah, sure, because the two are very closely related to each other. This one is the simpler 2-dimensional cousin of Stokes' theorem. So this is then also a precursor to the curl. It's just that I'd rather have the curl burned into my memory, because that's the thing that we will need to use all the way through physics. This one is just something that we can derive from that. In terms of a proof, well, if we prove it from Stokes' theorem, we first note that the standard parametrization of a 2-dimensional region, when I put it into 3-dimensional space as d cross 0, where I just put an artificial 0z component on there, is that surface of x and y is just x, y, 0, and if you, with xy being in D, so I'm not going to change anything there in terms of trying to figure out how to parameterize D, then I get that the x partial cross the y partial of this parametrization, well, the x partial is the first unit vector and the y partial is the second unit vector, right? dx is 1, and then you get zeros, and dy is 1, and the other components give you 0. And the cross product of the first unit vector with the second unit vector, you can just look at that with 3 fingers or compute it directly. Well, you get first component 0, second component 0, third component 1. So this is 0, 0, 1, which is the unit vector in the z direction. Well, that means that now the integral over the curve of the vector field pq.dc is the integral from a to b of p of x of t, q, y of t, q of x of t, y of t, x prime, y prime, dt, which of course is the same as what I get when I take the integral of p of x of t, y of t, q of x of t, y of t, 0, and x prime of t, y prime of t, and 0, and then go ahead and work that out. And that is now the same as the integral in 3-dimensional space of the vector field pq0.dc. That's now the explicit parametrization, right? And this thing I can apply Stokes' theorem to. So this is now the integral over an interpolating surface of the curl of this vector field G here. Let's just call that thing G dot ds. And that gives us that we have the curl of this vector field. Well, let's see. The first and second component actually don't matter, because they are multiplied in a dot product with the unit with the normal vector of the surface. So that's just 0, 0, 1 dA, whatever the area element is for your domain. And that means we really only have to worry about the third component, and the third component is dq dx minus dp dy. And so that then gives us the integral over the region dq dx minus dp dy dA as it should be in Green's theorem. And that finishes the proof of that result. And now we can look at an example. Well, first let's be careful with notation. Green's theorem is also often stated as the closed line integral of p dx plus q dy is equal to the area integral over the enclosed region D of dq dx minus dp dy times the area element dA. This notation, I didn't push it very much in the line integrals, because actually the other way to set up the line integrals that we've used is physically a whole lot more intuitive as far as I can see. And so that is just something where we need to be able to read the notation that's going to come back to us when we compute area with a line integral. So, as an example, compute the integral of the vector field f of xy being x squared and xy over the positively oriented boundary of the triangle with vertices at 0, 0, 1, 0, and 0, 1. Well, rather than computing 3 line integrals, because we'd have to have the segment going left to right, then right to left going up, and then back from the top back down to the lower left corner, rather than doing that, we use Green's theorem, which means we have to replace the line integral in an xy coordinate system from 0, 0 to 1, 0 to 0, 1 and back along this line, and that line with an area integral over the area of the triangle, which means that the integral of PQDC is actually the integral over the triangle D dq dx minus dp dy dA. The integral over the triangle is that x goes from 0 to 1. Y then goes from 0 to this line here, which is 1 minus x, so 0 to 1 minus x. dq dx is d dx of xy minus dp dy, which is d dy of x squared, dy dx at the end. The integrand is y minus 0, so this is just the integral from 0 to 1, and from 0 to 1 minus xy dy dx. Well, that's easy to work out because that's the integral from 0 to 1 of 1/2 y squared from 0 to 1 minus x, which is the integral from 0 to 1 of 1/2 1 minus x squared, which is the integral from 0 to 1 of 1/2 times 1 minus 2x plus x squared, which ends up being, hey, I think I lost a negative sign here. Hang on just a second, please. And indeed, I did lose a negative sign, but now it is fixed. Let's go through this again. We have 1 minus x quantity squared, which is 1 minus 2x plus x squared. If I multiply that with 1/2, I get 1/2 minus 1/2 times 2x, which is minus x, plus 1/2 x squared. And of course, that's easily integrated. That is an antiderivative of 1/2 x, because we just have the antiderivative of 1/2, minus 1/2 x squared, which is the antiderivative of x, plus 1/6 x cubed, which is the antiderivative of 1/2 x squared, from 0 to 1, where we get 1/2 minus 1/2 plus 1/6, and the result is 1/6. So this works very similar to Stokes' theorem because, as we know, it is a cousin of Stokes' theorem. The really neat application is that you can actually compute area with a line integral, which sounds really, really funky, but it does work. Because here's what we can do. The area of a region is nothing but the double integral of the function 1 over the region itself, right? That is something that I think we also talked about when we did double integrals and triple integrals. The volume of a region is the triple integral of 1 over the region itself. But 1 can be written as dx dx minus derivative of 0 with respect to y, and that now can be interpreted as a q and a p in Green's theorem, and that means this is the same as the integral over the perimeter of our region D of the vector field 0x dot dc, which is the same as the integral from a to b x of t y prime of t dt if we use a parametrization, or in the notation, which here is very prevalent, and so I'm not going to avoid it here. It is the integral over the closed perimeter of x dy. Similarly, as a corollary, if we have P, a curve in the plane that is positively oriented, piecewise smooth, simple, and closed, and if D is the region in the plane that is bounded by this positively oriented perimeter curve P, then the area of D is A equals integral over the perimeter x dy. Similarly, it is the negative integral over the perimeter of y dx. That's where you simply put the vector field in the y derivative. It's the same derivation as before. And of course, if something is equal to two quantities, then it's also equal to the average of these two quantities. So it's also sometimes written as 1/2 of the perimeter integral of x dy minus y dx. And that is something that then leads to a fairly simple computation of the area of an ellipse. So if I take a general ellipse, x squared over a squared plus y squared over b squared equals 1, and I want to compute the area, I can do the following. The perimeter is parameterized by the standard perimeter curve, which is a cosine t, b sine t, right? It's polar coordinates only with different radii, so it's the parametrization of a circle with two different radii, which sloppily speaking is what an ellipse is. And that means I can write up the area as the integral of x dy, well, x is a cosine t, and dy would be the derivative of b sine t. So the rest is now just computation, because now to parameterize it, I need to integrate from 0 to 2 pi, because I have to go all the way around the perimeter, of a cosine t times the derivative of y prime dt, which is dy, right? dy is y prime dt. So we end up with b times sine t prime, and that is nothing but a integral from 0 to 2 pi a cosine t b sine t dt, which is ab integral 0 to 2 pi cosine squared of t. And if we work that out with trig identities, we realize that the cosine squared of t is 1/2 1 plus cosine 2t, because what happens when you square is everything is flipped up, which is like a doubling of the frequency, but at the same time it now has only an amplitude of 1/2 around the height y equals 1/2, and because it starts at 1, it's then a 1 plus cosine 2t rather than a 1 minus cosine 2t, which would be the sine squared. Either way, if you've just memorized this identity, it gives you the same thing. And of course, this is now quick to integrate. We have ab times the integral of 1/2 times 1 is 1/2 t. The antiderivative of the cosine of 2t is 1/2 sine t, and this 1/2 gives us the 1/4. Yeah, okay, the integral of cosine 2t is 1/2 sine 2t, and with this 1/2 you get 1/4 sine 2t. It turns out that that ultimately doesn't matter, because now if you plug in 2 pi, you get 2 pi times 1/2, which is pi, plus 1/4 sine 4 pi, which is 0, minus 1/2 times 0, minus 1/4 times sine 0, which are all 0. So you end up with ab times pi, which is indeed the area of an ellipse. So, as the conclusion for our excursion into vector calculus, and in many ways as a conclusion to our capstone of calculus, another quick presentation. Like I said, we definitely have earned that by working our way through the divergence theorem and Stokes theorem. We had another presentation that allows us to hopefully further work with these theorems and appreciate them. And as a sideline, we've got a really neat little application, which is that we can compute areas with line integrals, which feels like a paradox, but as we can see here with the area of an ellipse, it works rather well. All right, hit some homework problems on Green's theorem to make sure you're on top of this one also. And other than that, congratulations. If you have followed this course in the way I've outlined it, you are done with vector calculus. Sometimes in my outline I put optimization near the end, so you may still have to do that, but I can tell you, you have gotten over the hump. This is the pinnacle. If you fully understand Stokes theorem and the divergence theorem, as well as its consequences and the divergence, the curl, and the gradient operator, you pretty much have a command of everything that calculus does, because all the computations involve the computational parts of calculus, the visualizations involve the visual part of calculus, including graphing at some point in time. The one thing that is a little bit missing is optimization, which you either still have to do or maybe you've already done it. Either way, congratulations.